Alright, I just wanted to mention, what happens if we start with the sodium hydroxide in the container and we slowly add HCl? Well, what we're going to get is we're going to get a pH curve that's going to do this, where we start with a strong base. We're still going to get a really, really similar vertical jump. A couple of things to note. One, at this point out to here, what we're going to be looking for is how much excess hydroxide ion. We're still going to do stoichiometry the same way. We're still going to account for the additive volumes, divide to find the new molarity. The biggest thing we have to remember is the molarity of this is the molarity of the OH, which if we do the negative log of that, we're going to have to subtract from 14 to find the pH. And then at the equivalence point, we're still going to have a pH of 7. And then once we pass that and we work this problem on out, for the remainder of the problem, now we're going to have excess H+. Again, you still have to account for your additive volumes, but at those points you're going to be able to take your molarity of your excess H+, negative log, and get your pH. So how does it change things when we switch this to a weak acid and a strong base? So here we've got acetic acid represented by the Legos that I have here, and again the white sheet of paper is going to be my 1 liter container, and over here to the side these are my sodium hydroxides that I'm going to slowly add as we go through this titration. So first off, if I wanted to find the pH of this, in order to find the pH of this solution, even though there's 4 moles per liter of acetic acid, there's not that much H+ because it's not a strong acid. So I would have to go through an ice problem using a Ka value and see just how much, and again I'm going to represent this with 1, which is 25% ionized. It's not near that high, as we'll see as we go through the problems here in a moment, but we'd have to find how much H+ we truly have in solution. So it's just a small amount, and we would do an ice problem with a Ka and maybe use quadratic formula, maybe not. I'll talk a little more about that as we move on through the video. I'm going to try to show you ways to get around the quadratic formula. From a standpoint of AP chemistry, it's not necessary to use it, so I'll show you when you could and when you don't have to, and ways you can kind of sidestep that by way of the calculations. So what happens now when I add in a sodium hydroxide? Again, we're going to assume no volume change here. So I'm going to get sodium with this acetate ion, and I'm going to form a water molecule, but in doing that, when I start going through the equilibrium part of the problem, then I'm going to get some more ionization. And the question becomes, just how much more of that will ionize? And on top of that, aside from how much more that we'll get that will ionize, how much of this acetate ion? Because we're going to learn here in a moment that acetate ion is a conjugate base of this weak acid, so it also contributes to the pH. What we basically get, what we essentially get as we go through this, is when we're titrating a weak acid, in this case with a strong base, is we start forming a buffer solution. We start forming a solution where we have common ion effect that we have to go through with our ice problem in order to solve. Moving on with stoichiometry, if I throw another sodium hydroxide in, assuming no volume change, sodium acetates again stay ionized. This binds up. In binding that up, there's a small amount of H+ that contributes to the pH of that solution. And we do the calculations, and we also account for the conjugate base, the acetate ion. Also at this particular point, we're halfway to the equivalence point, and that's really, really important in terms of AP chemistry. A lot of common questions come from, what happens when we titrate halfway to the equivalence point. Now, the way we knew we were halfway, stoichiometry. We had 4 moles of acetic acid to start. We've placed in 2 moles of sodium hydroxide, same volume, and so we're halfway to the equivalence point. Again, we'll talk about that mathematically here in a moment, just showing you kind of representations here. What happens now is we get some more water formed, we get a greater amount of acetate ion, and we get a little more ionization. And what happens next? Well, next we reach what's called the equivalence point, but it's a little bit different than what we see when we're doing a titration between a strong acid and a strong base, because now What we have at this point is we don't have that H plus present, but we do have an ion here that's a conjugate base. So we actually have something that is basic. We form a salt, sodium acetate, that is basic. So at the equivalence point, we're going to have to address that. What kind of things are we going to have to do mathematically? It's going to be an ice problem. We're going to have to find a Kb for that base, and we're probably going to use the Ka for acetic acid in order to do so. So there's a lot of math involved at that particular point as well. Again, I'll try to simplify that. I'll do a few with quadratic formula, and then I'll show you why there's times you can ignore using quadratic formula in these solutions as well. Let's take it one step further. Let's throw in one more sodium hydroxide. So now we get this extra sodium hydroxide. Now the hydroxide ion is the predominant factor. In theory, this is a base. In theory, it's definitely a base, but its contribution to the overall pH is nowhere near what we get from that added strong hydroxide. So even though in theory we could do an ice problem, we would be putting in a common ion of hydroxide, which takes something that's already a weak base. It becomes a less ionized base because we've added a common ion, and really the predominant factor is the OH minus. It's not bad to note that you got base and base, but in theory, this becomes much less of a factor once we have the excess hydroxide. So how do we find the pH? Take your excess hydroxide, find your volume, find your concentration. Because it is hydroxide ion, negative log that value, subtract from 14, and you'll have your pH at that point. Alright, so you can see here I'm going to do several calculations where we find various pHs along the way of this titration. We've got 10 milliliters of 0.5 molar acetic acid. We're adding 0.8 molar sodium hydroxide. We're going to add none, and then I'm going to add this really small amount. And this is a point that I did not do in the last one. I'm going to do it here and just talk about it briefly and kind of what you run into mathematically. I'll set it up, I'll solve it quickly, but definitely want to focus more on these points down below. Much more important. You definitely have to be able to do no base added. That's just finding the pH of that solution. But then you definitely want to be able to do all of these. This one, I'll show you why we run into some implications there just so you're aware of it, but definitely we don't want to get hung up on the mathematics behind that. So what do we do if we have a 0.5 molar acetic acid solution and we want to find its pH before we add any base at all? Well, because there's no reaction, I don't have any stoichiometry to worry about. I'm going to go straight to dealing with my 0.5 molar acetic acid solution. And because I'm using that and I don't have any reaction, I'm going to jump right to my equilibrium reaction. And I'm going to start through an ice table where I have none, none, up by x to bx, up by x to bx, and down by x to be 0.5 minus x. Alright, so I need a Ka value. The Ka value for acetic acid is 1.8 times 10 to the negative fifth. That would be given in the problem, equals x times x, or x squared, over 0.5 minus x. Now, real quick, for purposes of AP Chemistry, you can ignore this minus x because it's going to be a small amount. And if you ignore that, then all you got to do is cross multiply or distribute the 0.5, whichever way you see that, and then take the square root to get your H plus. So you can do this without doing the quadratic formula. The good news, you don't need the quadratic formula. I'm going to go ahead and do it both ways just to show you on this one what happens. If I do the quadratic formula, I end up with an A value of 1. My B value ends up being 1.8 times 10 to the negative fifth, and my C value is going to be negative, and it's whatever the product of 0.5 times 1.8 times 10 to the negative fifth is, and I get that one root is 0.00299, the other one is negative, can't have a negative concentration, so I'm going to get that x equals 0.00299 molar. What if I had just ignored the x without the quadratic formula? I'm going to distribute the 0.5, so 1.8 times 10 to the negative fifth multiplied by 0.5, and then I'm going to take the square root of that. and I get 0.003. So you can see there's not a real big difference here in terms of the calculations of using the quadratic formula versus not using the quadratic formula in this particular problem. Alright, so with that, how do I now find the pH? So I'm going to do negative log of 0.00299, and I get 2.524. So the pH for the first problem is 2.524. Notice it's not near as low as what the pH was for the same molar concentration of hydrochloric because it doesn't fully ionize. As a matter of fact, the percent ionization, that's H plus at equilibrium out of what we made that solution to be to start with, 0.00299, divide by 0.5 times 100, and we see that this thing is about 0.6% ionized, so really, really low amount of ionization, but again, it's still an acid, and stoichiometry still applies as we go into the reaction part of this.